Okay, in today's lecture, we're going to cover the section 3.2 material on some properties of determinants, which we introduced in our last section. So we'll see some properties of determinants that we started to hint at in the previous section, which will allow us to evaluate determinants for fairly large matrices by making use of row reduction. So the first theorem that we'll introduce in this section, Theorem 3.3, is how row operations on a matrix will affect the determinant of that matrix. So let's suppose that A is some square matrix, and we're trying to find its determinant. Now maybe A is a large square matrix and none of its rows and columns contain many zeros, so a cofactor expansion might be pretty difficult. But this theorem says if we would perform row reduction on our matrix, then as long as we keep track of what operations we're performing, those row operations won't significantly affect the value of the determinant. So let's see specifically what we have here. So in property A, we had seen this result for some specific matrices in the last section. If a multiple of one row of A is added to another row to produce a new matrix B, then the determinant of B is equal to the determinant of A. So I can add or subtract scalar multiples of two rows of a square matrix, and the determinant of the new matrix that I get will be the same as the one before I perform that row operation. Now the second type of row operation we can perform is interchanging two rows. So if two rows of a matrix A are interchanged to produce a new matrix B, then the determinant of B is equal to the negative of the determinant of A. So that is, if I interchange two rows of a matrix, that would make the determinant of that matrix change in its sign. And lastly, the third type of row operation is if one row of a matrix is multiplied by a constant k to produce a new matrix B, then the determinant of B is equal to k times the determinant of A. So if I multiply a row by some constant k, then I have to multiply the, or I have to factor that constant k out from the determinant of the matrix that I had begun with. So as an example of this, let's look at how we could easily find the determinant of a matrix by applying some row reduction. So here, this theorem is going to enable us to evaluate determinants by row reducing some given matrix to a triangular form, that is upper or lower triangular. And we saw at the end of the last section that to find the determinant of an upper or lower triangular matrix, we just take the product of the diagonal entries. So let's take a look at this first example. We want the determinant of this 3x3 matrix. And we could get this through a cofactor expansion along one of the rows or columns. But we see that none of the rows or columns contain zeros, so a cofactor expansion can be a little bit tedious. Now instead, if we make use of row reduction, the determinant of this matrix, 3, 3, negative 3, 3, 4, negative 4, and 2, negative 3, negative 5, would be related to the determinant of a matrix in triangular form, or row echelon form. So one operation that I could perform here to try to put this matrix in row echelon form would be to make this leading coefficient in my first row a 1. And an easy way to do that here is by noticing that my first row, the entries in that first row, are all multiples of 3. So if I were to multiply my first row through by 1/3, or equivalently divide through by 3, I would have the constant 3 times the determinant of the matrix 1, 1, negative 1, and then let's see what other row operations we could perform in this step. So what I've done to get the original matrix A from this new matrix, I would have to multiply the first row through by 3. So equivalently, we can think about factoring out that constant 3 in front of our determinant here. So we're making use of property C from Theorem 3.3. Now in this same step, I might want to eliminate the leading coefficient of 3 that appears in the second row. And I could do that by taking my first row, multiplying by negative 1, and then adding it to the second row. So using property A of Theorem 3.3, that says it would not change the value of the determinant. So if we perform that operation, we would have 0, 1, and negative 1. And for right now, I'm going to leave my third row alone. We've got 2, negative 3, negative 5. So at this stage, I have a 1 as the lead coefficient in my first row, 0 below it, and then I need to eliminate this leading 2 in my third row. So to do that, I could multiply my first row through by negative 2 and add it to the third row, and let's see what that gives us. So we know by property 1 of Theorem 3.3, that sort of row operation would not change the value of the determinant. So we still have our 3 times the determinant of 1, 1, negative 1, 0, 1, negative 1. And performing the indicated operation, we would have a negative 2 plus 2 is 0, negative 2 plus negative 3 is negative 5, and then a positive 2 minus 5 leaves us negative 3. So now my first column is exactly as I want for row echelon form. I've got a 1 as the leading coefficient in my second row. So to put this in triangular form, well, I just need to eliminate the negative 5 that appears in the lead coefficient for that third row. So here we have 3 times the determinant of 1, 1, 1, 0, 1, negative 1. And to eliminate that 5, I could take 5 times my second row, add it to the third row, and that wouldn't change the value of the determinant according to Theorem 3.3. So let's see what we have. We would have 0, 5 minus 5 is 0, and then negative 5 minus 3 leaves me with negative 8. So at this stage, the matrix that we're taking the determinant of here has upper triangular form. So the determinant would just be the product of the diagonals, and then remembering we have a factor of 3 out in front, our determinant is 3 times the product of the diagonal entries is negative 8. So we're left with negative 24 for the determinant of this matrix. All right. Now, of course, we could have gotten the same result by applying a cofactor expansion along one of our rows and columns. And in this case of a 3x3 matrix, maybe that would be an easier approach here, a little more time efficient. But for larger matrices, we see that this row reduction method is usually the easier approach. So let's look at some other examples. In this next one, we have a 4x4 matrix, and we're told to find the determinant by row reduction to echelon form. So let's take a look here. We have we want the determinant of this matrix. And my first 2 rows are already in a form that I like. I've got 1 for the leading coefficients. So using the leading 1 in my first row, I can eliminate the positive 2 and negative 3 that appear below it in the third and fourth rows by taking a constant multiple of the first row and adding it to the third or fourth row. And using theorem 3.3, that wouldn't change the value of our determinant. So the determinant of A would be equal to the determinant of the matrix whose first row is 1, 3, 2, negative 4. Our second row is 0, 1, 2, negative 5. And to eliminate the 2 in that third row, I'm going to take negative 2 times the first row, add it to the third. So our negative 2 plus 2 becomes 0. We've got negative 6 plus 1, plus 7 is 1. We would have negative 4 plus 6 is 2. And then we would have a positive 8 minus 3 is a positive 5. And then to eliminate the negative 3 for the lead coefficient in our fourth row, I could take 3 times my first row and add it to the fourth. And that would not affect the value of the determinant according to theorem 3.3. So let's see what we have. We would have a positive 3 minus 3 is 0. Positive 9 minus 10 is negative 1. Positive 6 minus 7 is negative 1. And then a negative 12 plus 2 is negative 10. So now my first column is exactly as I want, 1 with zeros below it. And in my second row, I have this leading 1. I need to eliminate the positive 1 and negative 1 that appear below it. So to perform this, I could take my third row minus the second row, or equivalently take negative 1 times the second row and add it to the third, which doesn't change the value of our determinant. So the determinant of this matrix would be equal to the determinant of the matrix we get by subtracting those two rows, which would leave me 0, 0, 0, and 10. And then in my fourth row, I could add either the second or the third row to it to eliminate that negative 1. So here, if I add the third row to the fourth row, I have 0, 1, 0, 0, 1, and negative 5. So it's almost in triangular form. I've got 1 for these lead coefficients here. And then I notice that in my fourth row, I have a leading 1 that appears in a column to the left of the leading coefficient for row 3. So to get this in triangular form or row echelon form, I'm going to interchange rows 3 and 4. And remember that theorem 3.3 says if we interchange two rows of a matrix, that makes the determinant the negative of the matrix before we perform that operation. So this is then the negative of the determinant of our matrix, 1, 3, 2, negative 4, 0, 1, 2, negative 5, 0, 0, 1, negative 5, and 0, 0, 0, 10. So this new matrix that I'm considering is now in upper triangular form. So its determinant is the product of the diagonal entries, which we can see is 10, and then remembering that we have a factor of a negative 1 out in front, we have a determinant of negative 10 here. So of course we see, well, we could have obtained the same thing by maybe using a cofactor expansion down the first column since it contained a 0, or maybe across the second row. But then we're having to take determinants of 3 by 3 submatrices, which starts to get a little tedious. And here the row reduction was not very difficult. All right. Now, our next result, or the next property of determinants that we'll look at, is one that we've already explored a little bit in the previous sections. So this result, theorem 3.4, is now an extension from the cases that we had seen earlier, where we were working just with 2 by 2 matrices. and it says that a square matrix A is invertible if and only if it has a non-zero determinant. So a square matrix is non-singular as long as our determinant is non-zero, which means that an inverse does exist. And we've already been using that for the case of 2x2 matrices, but this theorem says that now holds in general for any square matrix. So this theorem 3.4 gives us another equivalent result for the invertible matrix theorem. It says any square matrix is invertible provided that its determinant is non-zero. So if we can show a matrix has non-zero determinant, then all of the other properties from the invertible matrix theorem must hold. So let's look at the following problem. Here we are asked to use determinants to determine if each matrix is invertible. So here in part A, we have the 3x3 matrix, and we could make use of row reduction here. But since this is a 3x3, and we see that we have a 0 entry in our third row or first column, a cofactor expansion isn't too difficult here. So let's consider the determinant of A by making use of a cofactor expansion down the first column. So we would have a positive 5 times the determinant of the matrix -3, -2, 5, 3. Then minus 1 times the determinant of the matrix 1, -1, 5, 3. And then plus, well, the last entry in that first column is 0, so I don't care what the cofactor is for that term. So we are left with a 5 times -9 minus a -10, or plus 10. Then minus 1 times 3 minus a -5, or plus 5. So we have 5 times 1, which is 5, and then minus 8, or -3 for our determinant. And we see here that this determinant is non-zero, so the matrix A is invertible. Or equivalently, we could say that A is non-singular. It does have an inverse. So let's look at another one. In part B, we have the following matrix 2, 3, 1, -1, 2, 1, 4, -1, -1. So again, it's a 3x3. It's not terribly difficult to use a cofactor expansion for 3x3s. So let's stick with that approach rather than row reduction. Usually row reduction is only a better approach if we've got a 4x4 matrix or larger. So here, the determinant of the matrix B, using a cofactor expansion, say, along the first row, would be 2 times the determinant of 2, 1, -1, -1, minus 3 times the determinant of -1, 1, 4, -1, and then plus 1 times the determinant of -1, 2, 4, -1. So this leaves us with 2 times -2 minus a -1, or plus 1, minus 3 times 1 minus 4, and then plus 1 times 1 minus 8. So altogether we have a 2 times -1 is -2. Our -3 times -3 gives us a plus 9, and then 1 times -7 is -7. So we're left with 9 minus 9, which is 0, and a 0 determinant means that the matrix B is singular. an inverse does not exist according to Theorem 3.4. All right. Now we could also make conclusions about the matrices A and B, such as do their columns span R3? Well, for matrix A, yes. For matrix B, no. If we think about consequences of the invertible matrix theorem. So once we are able to calculate determinants, we can make certain conclusions about properties of our matrix by making use of that theorem. So let's look at a useful corollary to Theorem 3.4. So this theorem implies that the determinant of a matrix A, a square matrix A, is 0 when the columns of A are linearly dependent. So that is a result which follows directly from the invertible matrix theorem. So if we want to know whether a set of vectors is linearly independent or dependent, we could put that set of vectors into a matrix and consider its determinant to see whether it is 0 or non-zero. Now, another result, we can say, moreover, the determinant of A is equal to 0 if the rows of A are linearly dependent. So why would that be true? Well, again, it follows from the invertible matrix theorem. The rows of a matrix A would be the columns of A transpose, and linearly dependent columns of A transpose would make A transpose singular. Now, if A transpose is singular, then the invertible matrix theorem says so is the matrix A itself. So if we have a zero determinant, that means that our rows of a matrix would be linearly dependent. Now this, in practice, is usually obvious when we have two rows or two columns of a matrix which are identical, or a row or column of all zeros. So we know in the case that two columns are identical, or maybe one's a non-zero scalar multiple of the other, then those vectors are linearly dependent, and that would immediately imply that the determinant of our matrix is 0. So let's look at an example of this. In the following problem, we're asked for the determinant of this 4x4 matrix. And there's a few ways we could do it now. We could take a cofactor expansion down the first column or second row, since it contains a 0. We could maybe work with the fourth row or the third column, since it contains a 0. Or we can use this row reduction algorithm. We could try to reduce this to a triangular form, and then use our result from Theorem 3.3. So let's try that approach here. We're looking for the determinant of the matrix 3, -1, 2, -5, 0, 5, -3, -6, -6, 7, -7, 4, and -5, -8, 0, 9. So in order to try to move this towards triangular form, well, we have a leading coefficient of 3 in our first row. I've got a 0 below that. And so let's, in this first step, try to eliminate the -6 that appears as the lead coefficient in that third row. We can use that leading 1 in our first row to easily accomplish that. So taking 2 times my first row and adding it to the third row would not affect the value of the determinant of the matrix according to part 1 of Theorem 3.3. So let's see what we have when we perform that operation. Our first 2 rows will remain the same. And our third row becomes, let's see, we've got 6 minus 6 is 0. -2 plus 7 would be 5. Positive 4 minus 7 is -3. and then a negative 10 plus 4 is negative 6. And for now, I'm going to leave my fourth row alone. So we could keep proceeding here to try to reduce this matrix completely to row echelon form or triangular form. But at this stage, after performing that first step in our row reduction, we see that our second and our third rows are identical. So if we have two rows or two columns of a matrix which are the same, that means that the vectors which form those two rows or columns are linearly dependent. And the invertible matrix theorem says that if we have linearly dependent vectors as the rows or columns of our matrix, the determinant must be 0 since it does not have an inverse. So here we can say the determinant of our matrix is equal to 0 since rows 2 and 3 are linearly dependent. So as we're performing our row reduction algorithm on a matrix and keeping track of its determinant, if at any point we see that two rows or two columns are identical or scalar multiples of each other, then we immediately know that our determinant is 0. Okay. So in this next example, we'll consider finding a determinant of, again, a 4x4 matrix. And the primary methods which we've now talked about to find a determinant are cofactor expansion or this row reduction approach. So in practice, when we're taking determinants of matrices, we might want to combine more than one of these approaches depending on what form our matrix has. So in this next example, we're asked to combine those two methods in order to evaluate this determinant. So here, there's several ways which we could proceed to start with. We might notice that a cofactor expansion along the second row would be fairly easy. We only have two non-zero entries. Or a cofactor expansion down the fourth column would be pretty easy. We, again, also have only two non-zero entries, both being 1 there. So here, either approach would be valid. Now, another approach which we could use would be to start by making a row reduction. If we compare the last few entries of rows 1 and rows 3, we see that they are identical. So if I were to subtract one row from another, I would only have one non-zero entry in that row, and I could then use a cofactor expansion. So let's use that approach here. So I would start by taking the determinant of the matrix that I get by subtracting row 1 from row 3. So my first row will remain the same. Second row, and when I subtract the first from the third, I have a 2, 0, 0, 0. And my last row I'm going to leave alone for right now. So I'll have negative 6, 5, 5, and 0. So now taking a cofactor expansion down the third, or across the third row or down our fourth column only involves one non-zero entry. So I'm going to work with it doesn't really matter which approach we use here. I might work with the cofactor expansion down the fourth column. So let's see what our initial sign is. We have a plus, minus, plus, minus. So we would have for our cofactor expansion a negative 1 times the determinant of the 3 by 3 submatrix we get by deleting that row and column. So we're left with 0, -2, -4, 2, 0, 0, and -6, 5, 5. So now at this stage, well, for the determinant of this 3 by 3, I could take a cofactor expansion across the second row since it only has one non-zero entry. So keeping track of our sign again here, well, we would start with a positive and then a negative. So I'll have my initial factor of -1 that we had out in front times the cofactor expansion for this 3 by 3, which would start with a -2, times the determinant of the 2 by 2 submatrix, -2, -4, 5, 5. So this then gives me a +2 out in front, and the determinant of this 2 by 2 submatrix is -10 minus -20, so +20, which leaves me with 20 for my determinant. So we can see here by maybe combining certain approaches, such as row reduction or a cofactor expansion, we can evaluate these determinants a little more easily than using any one approach. So in our next example, let's consider a problem relating back to linear independence or dependence. So we've just said that from theorem 3.4, a set of vectors, which are, say, the columns or rows of a matrix, are linearly independent if and only if the determinant of that matrix is 0. So going back to a question that we had looked at in chapter 1, if we ask determine whether a set of vectors is linearly independent, we can form a matrix A, which has these vectors as its columns. So 4, 6, 2, -7, 0, 7, and -3, -5, -2, and see whether this matrix has a 0 or non-zero determinant. So looking at our matrix to determine what approach we might use to find our determinant, well, it doesn't seem like row reduction is particularly nice here. I might interchange, say, my first and third row, and then use the resulting 2 to eliminate the 4 and 6 terms. But rather than making use of that row reduction, I also see if I were to use a cofactor expansion along the second row or the second column, it only involves 2 non-zero terms. So let's consider a cofactor expansion along the, let's go with the second column. So starting with our sign, we would have a plus minus, so taking the negative of this entry, -7, we have 7 times the determinant of the submatrix, 6, -5, 2, 2, then plus our 0 term, and then minus our +7 times the determinant of the matrix 4, -3, 6, -5. So we're left with 7 times a 12 minus the -10 is +10, and then -7 times our -20 minus a -18, so +18. And this leaves us with 7 times 22 minus 7 times -2. So whatever this works out to, certainly we know it's non-zero, which is all we care about for linear independence. So since our determinant A is non-zero, we can say the columns of A, which were the vectors, are linearly independent. They would be linearly dependent if and only if that determinant was 0. One note that I'll make before we move on to the next part of this section is from our Theorem 3.3, we saw that we can perform row operations on a matrix, and it affects the determinant in certain ways. Now, in our next theorem that we'll introduce, we'll show that we could perform elementary operations on the columns of a matrix if it were easier to manipulate the columns instead of the rows. And we have results which are analogous to the row operations which we've considered from Theorem 3.3. So this next theorem in particular will illustrate that our column operations have the same effects on the determinant of a matrix as the row operations. So this result, known as our numbered theorem 3.5 from your text, says that if A is a square matrix, say n by n, then the determinant of A transpose is equal to the determinant of A. So by performing column operations on a matrix, well, any column operation on A transpose is the same as a row operation of the matrix A. So it would affect the determinant in the exact same way, since these determinants are guaranteed to be equal. Now, this theorem has sort of an intuitive proof, which isn't as complicated, which follows from our result from section Theorem 3, or from our theorem that we saw in section 3.1, which said that a determinant can be determined by a cofactor expansion along any row or column. So if we look at a cofactor expansion down the first row of the matrix A, and then take a cofactor expansion down the first column of A transpose, well, that would be the exact same cofactor expansion, so those determinants must be equivalent. Sort of an intuitive idea there. So in the last part of this section, we'll look at some determinants of products of matrices, or then extended to powers of matrices. So our next result, Theorem 3.6, is sometimes called the multiplicative property of the determinant, which says that if A and B are square matrices, then the determinant of their product is equal to the product of the determinants. So in our next example, we want to verify that property for specific matrices A and B. So let's start by finding the determinant of each of these matrices. So here, the determinant of A, since it's a 2 by 2, is the product of our diagonals. So here, -6, minus the product of the off diagonals, which is also -6. So our -6 plus 6 leaves us with a determinant of 0 for the matrix A. So here A is a singular matrix. And the determinant of B is equal to -12 minus a -3, so plus 3, which leaves us with -9. So here the determinant of A times the determinant of B is equal to 0 times -9, which is simply 0. So let's now compute the matrix product A times B. So that was 3, 6, -1, -2 times 4, 3, -1, -3. So for our product, we get back a 2 by 2 matrix, and to find our first row, first column entry, we're taking the dot product of our first row and first column of these factors. So here we would have a 12 minus 6 is 6. For the first row, second column, we have 9 minus 18, so negative 9. For our second row, first column, we have negative 4 plus 2, or negative 2. And for our second row, second column, we have minus 3 plus 6. So a 3 for that last entry. So now, taking the determinant of this product, A times B, well, the product of the diagonals is 18, minus the product of the off diagonals is also 18, so we have a 0 determinant. Now we could have also seen the 0 determinant by comparing our first and second rows. We see that the first row is negative 3 times the second. So if one is a scalar multiple, that means those rows are linearly dependent, so the determinant must be 0. Or here for a 2 by 2 matrix, we could find it directly from our formula. So here it does follow that the determinant of A times the determinant of B is the same as the determinant of the product, A times B. So in this example, we see, well, if one of our matrices in a product is singular, well, it must have a 0 determinant, which means that by this multiplicative property, if we multiply that matrix by any other matrix, it must also have a 0 determinant and be singular. So we can state here, if we're taking the product of any singular matrix with another matrix, the resulting product must also be singular. So as another application of this multiplicative property, we can compute the determinant of matrices which are being raised to large powers. So say here the determinant of A, maybe just to the 4th power, where A is this 3 by 3 matrix. Now to compute that directly, before making use of the multiplicative property, we would have to find A to the 4th. So multiplying A by itself 4 times here is pretty tedious, and then we would have some 3 by 3 matrix which we need to take the determinant of from there. But by making use of the multiplicative property, we know that the determinant of a product of matrices, so say A to the 4th is just the product of A with itself 4 times, that would be equal to the determinant of A multiplied by itself 4 times, or raised to the 4th power. So let's look at the determinant of A. To calculate the determinant of A, well, we could use a cofactor expansion down the first, or across the first row of A. So here we have 1 times the determinant of 1, 2, 2, 1, minus 0. And then plus 1 times the determinant of 1, 1, 1, 2. So we're left with 1 times 1 minus 4, minus 0, plus 1 times 2 minus 1. So we're left with a negative 3 plus 1, or negative 2, for our determinant of A. So the determinant of A to the 4th power is then the determinant of A, which was negative 2, raised to the 4th. So we're left with a positive 16 for our determinant of A to the 4th. This is certainly much easier than first calculating A to the 4th and finding the determinant of the resulting matrix. Now in our last example, we'll talk about a linearity property for the determinant function. So we've just seen that the determinant of a product is the product of the determinants, and a common error or misconception is that the determinant of a sum, a plus b, is equal to the sum of the determinants. However, that is not true in general. The determinant is not a linear function. However, there is a particular case where the determinant is linear, and that is if all of the columns except one, or because we know the determinant of A transpose is the same as the determinant of A, if all of the rows of a matrix are held fixed, then the determinant of A is a linear function of that one vector variable. That is the one column or one row, which can be considered as a vector, which is being changed. So to illustrate this, well, suppose that we have a matrix A, and the jth column of that matrix A is allowed to vary. So maybe A has the following form. The first j minus 1 columns, or vectors A1 up through j minus 1, and our jth column is some value x. And then the j plus first column through the nth column are held constant. So if we define a transformation t from Rn to Rn by t of x is the determinant of this matrix A, then it satisfies the following properties. T of c times x is c times t of x, and t of u plus v is the sum of t of u and t of v. So that is, this transformation is linear, acting on that vector x, which is the single column of our matrix being allowed to vary. And again here, as I mentioned earlier, since the determinant of A transpose is equal to A, the determinant is a linear function if all of the rows of a matrix, except one, are held as fixed values. So in our last example here, we are asked to verify that the determinant of A is equal to the determinant of the sum of determinants of B and C, where A, B, and C are the indicated matrices. So notice that the second row for all three of these matrices is identical, CD. So only one row is being altered. And here the first row of A is the sum of the first rows of B and C. So we want to verify that that linearity property for the sum holds true here. So let's start by looking at the determinant of A. We would have, for the product of the diagonals, A plus E times D, minus the product of the off diagonals is B plus F times C. So expanding, we have AD plus ED minus BC minus CF, or FC. Now, the determinant of B is given by AD minus BC, and the determinant of C is given by ED minus FC, or CF. So taking the sum of those terms, determinant of B plus determinant of C, we have AD minus BC plus ED minus FC, and that is exactly the same expression that we found above. Comparing their terms individually, we have our AD minus B times C plus E times D, and then minus C times F, or F times C, it doesn't matter. So here we have the same value for the determinant of A, and the sum of the determinants of B and C, where the second row of these matrices is identical. So linearity holds for the determinant only if a single row or a single column is being manipulated. So that finishes this section 3.2 material on some properties of determinants here. We get a few nice properties which allow us to find the determinants of fairly large square matrices by using row reduction, maybe combined with the cofactor expansion. We've seen that the determinant of the transpose of a matrix is the same as the determinant of the matrix. We've seen that a non-zero determinant guarantees that our matrix is invertible, so therefore gives us all of the properties from the invertible matrix theorem. And we've seen that one of those properties in particular is in determining linear independence of a set of column vectors or row vectors. If we put those vectors into a square matrix and take the determinant, as long as that determinant is non-zero, the given set of vectors must be linearly independent.